So in this video, we're going to talk about some special cases of solving 3x3 systems. So when we're talking about solving systems of three equations, remember that we're actually trying to figure out the intersection of three planes. So remember that systems like the ones we've seen so far with one solution will intersect at a point represented by an ordered triple. So we can also have systems that have infinite solutions. So if our three planes intersect in a line, we can have a system with an infinite number of solutions because lines have an infinite number of points, right? So if all three planes intersect at a line, then every point on the line is going to be a solution. Also, we can have systems that will intersect in the same plane. So every point on the plane then will be a solution to the system. And remember that a plane contains an infinite number of points. We can also have different situations that lead to a system with no solution. So if just two of our planes intersect, but then all three don't intersect, we can have no solution. Or we can have a situation where none of the planes intersect, and that also leads to no solution. So we're going to still work on solving these systems algebraically in this video. So we're going to start off by using a lot of the same steps. We're going to decide which variable to eliminate, and then combine the two equations to eliminate this variable. Then we're going to combine a different pair of equations to eliminate the same variable, and then solve the resulting 2x2 system whenever we can. So let's look at this example. So let's start off by solving the system. So remember, the first step is to always look at your system and decide which variable to eliminate. So I think that x looks like a good variable to eliminate, so I'm going to go ahead and number my equations. So I'm going to start off by combining equation 2 and equation 3. So equation 2 is 2x plus 5y plus 4z equals 8, and equation 3 is negative 4x minus 10y minus 8z equals negative 16. So since I want to eliminate x, I'm going to go ahead and multiply the top equation by 2, so that gives me 4x plus 10y plus 8z equals 16. So when I combine that with the second equation, negative 4x minus 10y minus 8z equals negative 16, well, these terms will cancel each other out. 10y and minus 10y will cancel, and 8z minus 8z will cancel, so I'll have 0 equals 16 minus 16, which is 0. So that gives me 0 equals 0. And what this is actually saying is that equation 2 and equation 3 have the same plane. So whenever I get a 0 equals 0, that means that these two represent the same plane. So I'm thinking that I'm probably going to have infinite solutions, but let me check a different pair of equations just to make sure. So now I'm going to try combining equation 1 and equation 3. So equation 1 is 5x plus 4y minus 5z equals negative 10. Equation 3 is negative 4x minus 10y minus 8z equals negative 16. So to eliminate x, I need to multiply the top equation by 4 and the bottom equation by 5. So that gives me 20x plus 16y minus 20z equals negative 40. And now I'm going to multiply everything in my bottom equation by 5, and that gives me negative 20x minus 50y minus 40z equals negative 80. So now I'm going to go ahead and combine these equations. So 20x and minus 20x, that'll make 0. 16y minus 50y, that's going to give me negative 34y. Negative 20z minus 40z is negative 60z. And negative 40 minus 80 is negative 120. Well, now you can see I have an equation in two variables, right? So I have two variables, y and z. So whenever we have an equation in two variables like that, that is actually going to represent a line. So if I try to visualize this situation, I'm going to kind of draw a sketch here. So equation 2 and 3 are going to be the same plane, right? But that's what we discovered. So that's why I'm going to shade that in. And then we have another plane represented by equation 1 that intersects that plane in a line, right? So that line can be represented by that equation we found. So every point on that line is going to be a solution to our system. So since there are infinite points on a line, we're actually going to have infinite solutions to our system. Okay, so that's a special case that we have here. Now let's try solving this system. So first we're going to look at this and decide which variable that we want to eliminate. So I think that y would be a good variable to eliminate in this system. So let's go ahead and number our equations. So I'm going to combine equations 1 and 2. So I have 2x minus 3y plus 4z equals negative 7. And I have negative 6x plus 9y minus 12z equals 21. So to cancel y, I'm going to go ahead and multiply the top equation by 3. So I have 6x minus 9y plus 12z equals negative 21. And then I'm going to copy my second equation because I don't need to change it. Negative 6x plus 9y minus 12z equals 21. So when I combine these two equations together, so you can see 6x and minus 6x makes 0, negative 9y and plus 9y makes 0, 12z and minus 12z makes 0, so I have 0 equals negative 21 and plus 21, those also make 0, so I have 0 equals 0. So whenever I have that, that means that these two equations actually represent the same plane. So now let's see what happens when we combine equations 1 and 3, okay? Because we always need to combine a second pair to double check and see what's going on here. So when I combine these two equations, I have 2x minus 3y plus 4z equals negative 7. And 3 is 4x minus 6y plus 8z equals negative 12. So to cancel y, I need to multiply the top equation by negative 2. So I have negative 4x plus 6y minus 8z equals 14. And so let's combine that with the second equation. So 4x minus 6y plus 8z equals negative 12. And when I combine these together, well, negative 4x and plus 4x makes 0. 6y and minus 6y makes 0. And then negative 8z and plus 8z makes 0. So I have 0 on the left. And then 14 plus negative 12 gives me 2. So that is something that does not make sense, right? So that is complete nonsense. 0 equals 2. So that means that the system will actually have no solution, okay? So that's like a situation where we have, okay, let's see, the first two planes that we combined, 1 and 2, that's a plane like, you know, right here. Those two intersect everywhere. But then we have another plane that's like maybe down here, and those two, the combined plane and the third plane are never going to intersect, okay? So that's how we have no solution. So now you can go ahead and pause the video and try this example on your own. So when I solved this system, I decided to go ahead and eliminate x. So I first combined 1 and 2. So I did that by multiplying the first equation by 3. So when I did that, I got 0 equals 0. So I know that those two equations represent the same plane. And then I combined equations 1 and 3. And when I did that, I got an equation in 2 variables, and I know that represents a line. So every point on the line will be a solution to the system. So I'll have infinite solutions, right? So this is similar to that first example we did, right? Where we have two equations that represent a plane, and then we have a third plane that is going to intersect that at a line. So we'll have infinite solutions. So using linear combination and substitution, you can solve a system of 3 by 3 linear equations. When solving, you may encounter systems that have one solution, no solution, or infinitely many solutions.